You are able to see the slides, right?
Yes, sir.
Yeah. So anyway, so last class, we have started our impact craters. Okay, so last week, which is the most important geological feature which you can observe on other planets. Okay, and other thing is if you want to find out age of these other planets, so that is the geological ages, or if you want to find out any important, the events which have happened on other planets, say. So the only way is through this impact craters itself. Okay, and then wherever you go in any planets, Mars or any terrestrial planets or asteroids or anywhere, this impact cratering has been found out. And then now it is very well understood that this impact crater is it is something like fundamental thing, okay, for formation of planets and then the evolution of our solar system itself. So that's what the most important thing we understood in our last class. Okay, so then the simple crater, complex crater, so if you remember, right, so we have variety of craters are there. So one is a simple thing, then we have complex, then we have the multi-ring basins also. Okay, so like that variety things has been found out. And then the last class I told you, so the like the simple to complex crater transitions, it depends on what it basically depends on what. So like in a simple to complex transition craters, say, which is the one which controls this transition.
Impact velocity.
No, on a given other planet, say, like for Earth and if for Moon, say, whether that is the same, the velocity may be same, all other things may be same, say, but what is the one which controls the, this transition?
Gravity.
Yeah, gravity. Yeah, excellent. So gravity, I showed you that graph also last class. Okay, so this also I showed you. So these are the rings also, I already showed you. Then multi-ring basins, say. See what's the difference between a complex crater and a multi-ring basin? Of course, multi-ring basin is also complex only, but geologically, what's the difference between these two? So we told in the last class, right? The most important phenomena for multi-ring basin is yeah. So what's the difference between multi-ring basin and complex crater? See what happens in the multi-ring basin, so we made one very important statement basically. So in multi-ring basin, what happens? Can you see this one? See what is happening in multi-ring basins? I told you, right, in the Oriental basin and other things also.
Mantle uplift.
Mantle uplift. Okay, so please remember. So the mantle gets uplifted at the center. So what happens is, the lava or whatever, it may come up and then, so this also I showed you the very important, the definition. Okay, so this is for the Oriental basin, say. So here, at the center, you also will have mantle uplift and lava or whatever, so that also comes to the surface. Okay, so that is where multi basin also we told you. Okay. Then we have also discussed about ejecta deposit. So when something gets impacted, so some of the material gets flied off, and then that's what we are calling as ejecta. Okay, so all those things may follow, in these lines, and then it also may create, small craters, say, around our this one also. So this also we said. And finally, there are some empirical relations also are there, like how much will be the ejecta and other things. Of course, we will come to that one. And then what is the mass of this ejecta, how much it comes out, and all those things we discussed in our last class. Okay, and then these very important things, ballastic sedimentation. Okay, it's a very important terminology used in the craters. So when there is a impact, so you will have these ejecta curtains actual. Okay, so there's a ballastic this so the material flies off, say, and then falls at some other place. So this they call as a ballastic sedimentation also. Okay, so this also in it has been found out, and how much distance it can go. So those things also have been very well understood in impact cratering. So this also is an impact ejectas. I showed you in the last class, where the most important this ejecta, most of the ejecta will be near the rim itself of the crater, and of course far away you will see all these things itself. Okay, so this also I showed you. So as distance increases, so what type of things you will find out one near a crater itself. And then, we also said what is the mass of the largest, the largest mass which gets ejected when there is a crater formation. And I showed you this meteorite craters, Arizona crater, people have established also, all these rules itself. And then when there is, of course, the impact, as already I mentioned you, it's not same. So Mars, when there is impact, is because Mars has water, you will see this type of fluid as ejecta also. Okay, so this also is a very important thing which differentiates, how the craters forms on variety of planets. Okay, secondary craters also we discussed. Then oblique impact is there. Then what happens? You will see these type of things itself. It is no more circular thing. Maybe some other complicated shapes. You can see on other planets also. And now coming to this scaling losses. Of course, I told you briefly in the last class. Like we would like to find out the inverse problems. Like for example, on moon, you have found out a crater, its diameter of the crater, rim depth, everything you have measured from your QGIS software. So obviously, you see, we will ask the inverse problem. What was the size of the impactor? What was its velocity? What was the angle? And what was the density of the material? Which has created that shape itself. So this is what we call as a, the inverse problem. Or sometimes we also would like to know the forward problem. So let us say tomorrow, if some size of the asteroid, its velocity, this thing, what will be the, how much crater will get, what's the diameter of the crater, what will be the depth of the crater, that also we may be interested, the forward problems and this inverse problems itself. So these things can be easily be found out from this scaling laws. Okay, so these are very important things in our impact cratering. So basically now if you want to follow the forward problem or the inverse problem, say, now here, the mechanics, that is the computational models are, of course, I showed you some videos in the last class, some computational models I have showed you, but now also, handling this impact problems, it's extremely difficult from computer as from analytical point of view, because the velocities are hypersonic, 17 kilometer per second or whatever, then, the material flies off, and then it is not like a solid or a liquid, and it will be in a hydrodynamic state, and the shock waves will be there, you followed. So it's extremely complex. So to model this one, and then if you want to answer, if you want to find out, say, if I give you the impactor size, angle, and its velocity, you can't predict the the crater dimensions and others from computational models. Maybe some now those models are there, but still it is not that simple, or the formation of the ring basins, or it's very difficult basically. So what one does is, they go for this type of scaling loss itself. It is a very simple methodology, which is widely used in our fluid mechanics and other things also. So the same thing they use to find out the scaling loss for the crater dimensions also. I don't know how many of you have known, any of you have studied this dimensional analysis in your undergraduate, have you heard this word, dimensional analysis?
Yes, sir.
Yes,
Where you studied? Which subject you have studied this dimensional analysis? That Buckingham pi theorem you would have seen, right? Where you have studied this dimensional analysis? Which subject you would have used this one?
Then physics.
in physics, sir.
In physics you have used, but in our civil engineering, so where do you use this dimensional? Very important. Yeah. So you would have used in hydraulics. I don't know how many of you remember, the fluid mechanics, hydraulics is it. So the dimensional analysis, Buckingham pi theorem, that becomes very important. Okay. So it is simple. So I will not go into detail, just to have a feel. I am just putting you like this is a pendulum. So, okay. Length is L and mass is M basically. Okay. Now you want to find out some type of a equation, or, you want to find out the time periods of this pendulum cell. So how do you find out time period of a pendulum? In dynamics you have studied, that yeah, I theta double dot plus you followed mg theta, sine theta is small, and then you write, and time period is, any of you remember what's the time period of a pendulum? From your dynamics class, if you remember the time period of a pendulum, so the expression.
2 pi root L by G.
2 pi root L by G, it's everybody knows. Okay, now to derive this equation, say, no need to write equations of motion and others. Okay, so the dimensional analysis also can be used. So dimensional analysis, what it does is, you make a list of all the physical variables and the dimensional fundamental constants. Say, So on which the answer could depend. So this is the first step. So now I want to find out time period of the pendulum basically. Okay, so my philosophy is I will find out the time period of a pendulum. Say, let us say I assume that in the time period of my pendulum depends on the length and then the mass basically. So this is my assumption. Say, okay, now write down the dimensions of these quantities. Like dimensions means, what is the dimensionality of length? Right, mlt to the power of -2 units and dimensions you have studied in your 12th class or 11th class itself. And then you demand on all these quantities, you should be able to combine a functional relation such that the equation is dimensionally correct basically. Okay, so this is the philosophy of dimension analysis. So now what we are trying to do, the time period of a pendulum say. So we are writing as, k is some constant, okay, which has no dimensions or something. So L is the length of this one and M is the mass basically. So now we are assuming the time period depends on is a proportional to L to the power of A and M to the power of B. And if I remove that proportionality, say K will come into picture itself. So A and B are the constants basically. So that you have to find out, by solving some type of equations or by equating. So what this dimension analysis says is you write down the dimensions basically. So anyway, K's dimensions are not, the K is a constant, okay, it is non-dimensionless quantity, and the length is, L basically, okay, so L to the power of A, and the time is seconds or T we write, and M is a capital M, so L to the power of A, M to the power of B basically. So this is how we write it. So now, what you have to do is you have to equate the dimensions. So the basic dimensions are mass, length, and time. You have studied in your 12th class itself. So MLT, that is what you do. Now you have to equate this side and right hand side. So here your left hand side has time and the right hand side has a length and mass itself. So what we try to do is now you have to equate exponents of M, exponents of L, and exponents of T on both the sides. So now on the right side, say what is the exponent of M? So it is basically B. Okay, so this, of course, I made a mistake here. 0 is equal to B, you have to write. Now exponents of L say, so that is, A is equal to 0 kind of thing you have. And then let me correct here itself. Yeah, so the exponents are something like this, okay. Yeah. So the exponents of M's on right hand side is, B, and on the left hand side, say there is no M itself. Here you are having only time itself, okay. So this is how the equation turns out to be. So now here, what is our meaning of this one? So what does it tells you in our dimension analysis, whether we are doing correctly or wrongly? So if we say the last one, it says 1 is equal to 0, whether it is possible. So it is completely, you followed, right, wrong itself. So in dimension analysis, say, so now if you do a mistake also, automatically it comes out. So what is that we have missed here? So time periods, it depends on length and mass we have assumed. But what is the most important, another quantity which we have omitted?
Time.
Time period of a pendulum. So time period of a pendulum depends on what are the quantities. One is mass and then length is there. Apart from that, what is other quantity you have to bring such that the equation has to be dimensionally correct? What is other quantity? So suppose the same pendulum is on Earth, same pendulum is on Moon, say, whether it will be same, the time period. See the same pendulum.
Gravity.
Now it depends on the gravity. Excellent. Okay. So this is what we have to modify the equation. So if you do mistake in dimension analysis also, automatically it turns out. So now we add this acceleration due to gravity and its exponent is C basically. So now we are having three things. A, B, C has to be found out. So now dimensionally, if we check, K anyway is a non-dimensional quantity. So L to the power of A, then M to the power of B, and acceleration due to gravity is LT to the power of -2 because it's a meter per second square kind of thing. So you put C, now you equate say. So mass left hand side is 0 and right hand side is B. Then L say, now we are having A and then C also will be there. A plus C is equal to 0. Then exponents of times, here it is 1. So T to the power of 1, that is this one. And here you are having -2 times C. So you solve these equations. So you will get C as -half and A as -half itself. So finally, my equation is T is equal to K is anyway non-dimensional thing, square root of L by G itself, which is same as the period of pendulum itself. And of course, you can get this constant K by some analysis, something you can do. But this is a basic philosophy. How do we do the dimension analysis? So dimension analysis, what we try to do is, you don't know the mathematics, say. So you don't know the complicated mathematics without going into all those things, just by intuitive feelings. First of all, you have to understand what are the all the variables which are involved here, and then you try to do this yeah, non-dimensional kind of a thing. You write a equation, like you said, the combined functional relation you have to find out such that equation is dimensionally correct, and then you equate the mass and then length and then time. These are the fundamental three quantities here, and then you solve it. So this is how you will get the solutions also. So this is what a typical dimension analysis one does, and it's a very popular in fluid mechanics. Everybody does that basically. Okay. Now even this dimension analysis is very important. When you are doing experiments also. So like for example, say if you want to find out that Oriental basin, say, which is I think huge 900 kilometers or 100 kilometer, the huge basin basically, and then you want to find out the inverse problem, like what was the impactor size, what was the velocity, say, and what was the angle at which that has struck the moon and then created this crater. So this is what you wanted to find out. Okay. Now what you do is the mathematical things and other things, you don't know, you don't have control, and writing those equations and solving it is a headache for us. So what we try to do is we do experiments in the laboratory. Okay. So you take some sand or whatever, you take some material, you do small scale experiments in the lab, because you cannot do 100 kilometers, that is not impossible. So you do experiments in the lab at a small scale basically. Okay. So now these things have to be extended to this Oriental basin or something like that. So there also we use this dimension analysis. Okay. That is a scaling basically from laboratory to the the exact thing itself. So in impact cratering mechanics, we use this dimension analysis only. Okay, we will not go into the details. I want all of you to at least understand, how these laws have been derived. Okay, so now if you see, this is a very simple methodology. Of course, the real situation is highly complicated, but for simplicity's sake, so these laws have been developed. The simple laws. Okay, like if I give the impactor size, if I give the impactor velocity, and if I give the impactor angles, how much will be the depth of the crater, or how much will be the diameter of the crater, the floor depth, like what will be the ejecta mass, what will be the melted ejecta, this one. So these equations have to be derived. So what people did in the olden days, that is in the 1970s or 19, at that time, computers was not that powerful. See, nowadays we have supercomputer, whatever simulations I showed you, last class on the impact, now people are able to simulate up to some extent. But in olden days, it was very difficult in 1978 and 79 and others. So what people used to do was, they used to do experiments in the lab. I think one NASA Gault or somebody, he was, he did a lot of experiments on craters, like he created some mud pits and then dropped several things, and then, he tried to do all this kind of dimension analysis, scaling, very simple equations he derived. And these equations, they work very, efficient or very excellent, they work very nicely when you apply these type of equations, say, for moon and other terrestrial planets also. So it is a very simple thing. We don't go into more mechanics like no shock waves, nothing, just a simple dimension analysis itself. So let us say we consider an impactor, say. So this is asteroid, okay, which is going to strike, and we are assuming that we are describing it in a very simple, we are assuming that all impactors are spherical kind of thing only. Okay, so it has a mass m, then velocity u, and then mass density, that is what type of material it is a delta. So these are the three variables, and we are assuming that impactor is spheroid, that is a sphere kind of thing. Generally it will be complex shapes, we are ignoring for simple dimension analysis. And then these three variables, you can find out the kinetic energy, and then the momentum, mass into velocity, then equivalent radius. Anyway, radius, right, the volume of a sphere, say that 4 pi 3 pi r cube or something like that. So these are the parameters, and the specific energy, you can give these type of things per unit mass. Then energy density, say, so you can give half delta into u square. So these are the things. So now in this crater scaling laws, all the impactors are assumed to be spherical. It have only three quantities are there: mass, velocity, and mass density. Okay, and even the angle of impact is also, if you want, you can include also, but for simplicity's sake, people they ignore that thing also. So these are the three variables only. And then the mediums, where it is doing the impact, like if it is impacting on moons, we describe only by two parameters. One is the mass density, that is rho, that is the our planet basically, earth or moon, or where this material is impacting. And then the strength, basically, maybe strength you can express in terms of stresses, or because it's a hydrodynamic, kind of thing. We may use some other things also, but anyway, it's a strength kind of variable itself. And of course, gravity plays a major role. Okay, so three things are there. So the impact is happening on Earth, it is different. The impact is occurring on Moon, it is different because gravities are different also. So these are the main variables which influences your crater formations. Okay, so the impactor is 1, 2, 3. So three value: mass, velocity, and mass density. So three variables are there. Then here say density, strength, and then gravity itself. So you can see. So these are the variables here. So now in our so the dependence of the crater volume. So now we are interested to find out what will be the volume of my crater itself. Okay, this is what we are interested. Like here I told you, right? So this problem if you see say. So here we are interested to find out the time period. So what we are and what we wrote was it depends on length and mass basically. So that is how you have to formulate the equation. So here also we are interested in finding the crater volume, like how much the volume of the crater will be, or you can even directly work with the diameter or whatever. So right now just for simplicity, the crater volume say. So it depends on the 6 independent variables. So mass, velocity, and delta for the impactor, and then the medium says rho and y, the strength, and then the gravity itself. So now there is a Buckingham pi theorem. I will not go into details, but you can go through in Wikipedia and textbooks. So they explain this very nicely here itself. So there are several, you can, one is a mass set basically. So you have to define, the non-dimensional or these type of variables here. So we can define like this V into rho by M. So these are all non-dimensional, the kind of things we define. One is based on the mass set, the mass is same or something like that you can get. Then you can also define where there is no unique way of defining these, the equations here. Energy set is there. So based on the energy set, so you can define these variables. Then gravity set is there. Then we have momentum set basically. So in several ways, these non-dimensional quantities can be defined in the dimensional analysis itself. Okay. So if you see the mass scaling set, that means what we are trying to do is we have done the experiments in the laboratory. Okay. So like in a given target material, so you have a target material with strength must result basically when similar experiments. Okay. So same type of experiments if you conduct in the lab at fixed velocity, fixed impactor density, and gravity is varied as inverse cube. So you will get the same, the answer itself. So this is what the mass scaling does. So it is, so this one, so V proportional to M. So that means these quantities are constant. So pi 1 is a constant here. So V is proportional to M if you take, say, from these equations, we can derive these type of, the variables. So the most important thing is gravity and mass. It is something like this. Cube root comes from this mass scaling. Okay. So when you are trying to do same experiment, say, if velocity is constant, so if you do an experiment, if density is a constant, velocity is a constant, and then fixed impactor density, fixed velocity, say, and only, the gravity is varying, like for example, if you take moon and, the earth itself, okay. So now what's the difference between moon and earth, or moon and Mars or some other things if you try to do it this one. So the same velocity, same impactor density, but only the gravity is a different say. So how things go. So this gravity and mass are aligned. This cube root thing comes up. This is what we call as the scaling basically. Okay. So there are variety of ways are there. One is you can do this energy scaling. Like energy is constant. Then how things scales. So we are having several variables. Say like keeping the mass constant. Okay. So how the things scale basically. How the crater volume scales when you do this way, or if we keep energy constants, like we have done an experiment and you want to translate it to a real situation, and let us say energy you have made constant, then how things scale, or momentum, say if it is made a constant, how things scale. So like that, from this dimension analysis we will get several the equations are there. They are very simple, but just you have to work it out. Like I have told you, there's that alpha, A, B, C, and other things have been found out. Like you say, energy scaling. So then, independent of you. So this is how the scaling comes. E to the power of 1 minus alpha by 3, G to the power of minus alpha, So there you will get these type of equation, like mass scaling, strength scaling, gravity scaling, quarter root energy scaling. So this dimension analysis, you can do variety things itself. And lot of equations have been derived in the past itself. Now also people are using these type of equations itself. Okay. So these are some of the equations. Like you can see here. So this is somebody has derived in olden days. So this is a diameter, the crater diameter, say. So he writes 2.53 into E, that is energy of the impactor, by rho, that's the density of the target material, gravity is a 0.25. So if you know the energy and then rho and g, if you substitute here, you will get this crater diameter. So all these things have come up from this dimensionality, analysis itself. So here, there are, I think, this paper. So here you can see the graphs. So on the x-axis, it is, the log of crater diameter, okay, the crater diameter size and impactor mass. That is the mass of the asteroid, basically. So this they have found out, and this is valid for moon itself, okay. So now the impactor size is, so log, it is in log graph. If it is a 20, so you can find out is how much will be the diameter here itself. So many people have worked out, the most important person who did all the dimensionalities is Gault, actually. He's from NASA. So he derived a lot of experiments in the lab, and then he derived dimensionality analysis, and then he has derived a lot of the equations itself. So OPIC, so this is also one of the, I think, the earliest the equation. So you can see here for stone impact, say. So he has given the diameter of the crater. So he says it depends 9.24 into 10 to the power minus 3 k to the power of half mass, and then velocity, I think the density of the projectile, then cos theta, angle of the impact, So they have derived these type of a simple equations, and k, I think, maybe a non-dimensional constant. So you have to solve this equation, get k, and then if you substitute here, say, you will get the diameter of the crater itself. So this is what they call as the scaling laws, which has been derived from dimensional analysis without going into the exact mathematics like shock waves, those computer simulations, without going to that one. So these things have been derived along back itself. So there are a lot of these equations are there, like cube root scaling. Last class also I showed you. So all these things comes from the dimension analysis. Keeping mass constant, you will get one type of a scaling, like that people have done also. So this is also crater diameter. So this is also one equation, you see, which has come from dimension analysis only. So this is a transient crater, say. So DTC, rho p, this is a density of the projectile or the material, and project density of the material, that's the target, that is our planet, terrestrial planet. L is, I think, you see, the projectile diameter, VA is the velocity, G is the gravity of the planet, and then sine theta, say. So this is the angle of impact, actually. So this equation has been derived from dimension analysis, okay, like whatever I showed you see the previous slide. So these equations are very, very popular. People use these equations, say, so to calculate, the diameters and other things also. And I don't know how many have you seen. Last class I showed you that Earth Impacts website, right? All of you have seen that one.
Yes, sir.
So that so what is your thing? What is that you have observed in that that one also you remember? If you give the diameter of the projectile, you remember the density of the material, and then those things automatically it will give the crater dimensions. You remember? So now how all those that software say, whatever you are seeing this one, so that also has been derived from these type of equations only, the dimensional analysis on that Collins paper. If you see, so he has derived this type of empirical equations from that equations, he said. So that's how that web, he has made those things itself. Now, similarly, lot of scaling laws are there. So this is scaling for crater diameter, how much mass is melt, say. This also we have a scaling law. Then all those laws are available. Now, empirical equations are already there from dimension analysis, okay? So if you give the inputs, you will get the output, actually. And now you can even work it back and even calculate the inverse problem also, you can easily calculate. So like, all of you, maybe you can take an like assignment, say. All of you know that lunar crater, right? Lunar crater in Maharashtra. So you have seen, no, that lunar crater.
Yes,
so now, what is the diameter of the lunar crater? What is the flow? The diameter of the lunar crater easily in Google Earth itself. You can put our papers also 1.8 kilometers. Say. Now using this scaling laws, say, you can easily estimate, right? What was the the diameter of the impact? What was the size? What was the velocity? Say. You can use these scaling laws itself. Or even you can go to that Impact Earth program. No, that program has been that web program, say. It is basically designed for Earth itself, those equations. So you can even do the inverse problem, and you can easily find out what was the the crater dimensions and other things also. Okay, so you can even try those things also. And then that Ramgarh crater, says, or not Ramgarh, Dhalo, yes. So you have seen, right, that Dhalo crater also. Just So I will just show you, okay, so you can just try these things. So if you see the Dhala craters, okay, so you can see this Dhala crater.
Yes, sir.
Now, what is your comment? Tell me. By looking at this crater, say, what is your comment? What the lunar crater? If you compare this with the lunar, say, okay. So that lunar crater, yes, lunar lake. Okay, yes. So this is a lunar lake. You can see, right? So lunar lake, how it is? This crater.
So it's like ball shape, regular simple crater it
It
looks.
is something like it looks like a simple this one itself. Okay. So now what you have to do, all of you, now you know the diameter. Okay, the rim is there. So from here to here, you know the diameter. I think 1.8 kilometer or whatever is the diameter of this one. And you know the floor depth also. That other papers are there, right? In the JGR papers, they have given the details. Now what you have to do if you want to do the inverse problems, you all of you should go to that Earth Impacts, that website I showed you, right? Last class, that Oxford University or what that Collins website. So there you go, say you do the inverse problem and tell me, what was impactor size, what was the velocity, from this scaling laws itself. Okay, so this is one thing. And then Dhala, if you see, so it is a very complex. So now this is a Dhala crater. How it is looking like? What is the reason or you followed, right? What is that? Why this crater is like this? What is your opinion when you see this crater? See whether it is a perfect circular.
No, sir. Maybe initially it was ball shape and side there might be another small crater. Then it ejecta came due to
That is
gravity ejecta.
followed. That is one thing. Otherwise, also, you can also say that it may be what type of crater it could be.
Complex crater.
No, it is a complex only, but there is no complexities right here. Complex means in the center, what you have to do at the center place.
The central lift will, peak will be there.
Where it is a peak here, there is no peak right at the center portion. You understand? So now this could be maybe the impact may be inclined actually. It may be not a 90 degrees impact. It may be 10 degrees impact or 30 degrees impact. Say very parallel something like that. Maybe we don't know. You followed right. So all of you, what to do? This is a Dhala crater and then lunar crater. So you go to that using the scaling laws. Okay. That Collins paper or that Earth Impacts program, you can easily find out and do the inverse problem itself. Okay, in India. Now one more crater is there. Okay, that is I think Ramgarh. Ramgarh crater. This is in Rajasthan. Okay. So this is also a famous crater in Rajasthan. Can you see this? Visible? This
Yes,
Ramgarh.
yes.
So this is how it is looking like. You can see it is also looks like more or less you followed it circular kind of thing only. It looks more or less like our lunar crater only, but of course there is no lake or whatever here. So what you have to do is so this also you measure, of course I don't know what is this, some lake or something maybe there, that's a different issue. Okay, so now you can find out its dimensions. Okay, this Ramgarh crater and Dhala crater and then lunar crater, say you try to do the inverse problem. So from that Earth impact, say you try to measure and then you try to calculate. Okay, what was the size of the impactor and what was its velocity, which gave rise to this much crater diameter. Okay, and maybe you can find out. I think this Earth topography also. If you, I think in the QGS, I think you can get the floor to rim depth also, right? All those things. So you can see this Earth topography also. You can in QGIS, you can do it in 3D also, right? You can measure the depth of the crater also, as far as I understand. If you plot the topographic contours, you will easily understand the depth also. So now what you people do is, you try to do, so these are the three craters, so Lunar, then Ramgarh, and then, your Dhalo crater. Say. You try to estimate the scaling loss, and then, you verify. Okay, so this is your, you try, this as a nice assignment itself. So now let us go back to our, okay. Now, visible, right, the slides now.
Yes, sir.
Yeah. So now, so these are the scaling laws, simple laws, you can find out for all other things itself, okay? And now these also impact melt mass, basically, how much mass will be melted. So this also came from the scaling laws, just by dimension analysis. So people, what they do is, they do this type of works in the laboratory, say, and then, you translate it to the real field through a scaling, like, keeping the mass constant or energy constant or momentum is constant or whatever, then you can translate this one. So this is a mass of the projectile if it is MP, say, okay, that is a mass of the projectile means mass of your material itself, and theta may be the angle or whatever here, and epsilon m is a specific internal energies of Rankine-Hughes state or whatever. So now once, and if you put sine theta, you will easily get the mass of melted, how much mass will be melted, for this given material itself. So you can try with all these scaling laws itself, okay? So what I suggest all of you is, I will be sending that paper also. So you please go through that Collins paper and then try to do the inverse problem for these three craters, say. So you get me the, what was the input, basically, what was the size of the asteroid, velocity, angle, and others, or whatever. You try to get those numbers by using these type of scaling laws. And then the, the ejecta you followed, right? How much mass of the ejecta, so many equations are there. So all those things you try to get from this scaling laws also. So this also is very important, when you're studying craters on Earth, say, so our, the Mars itself, atmosphere is there, right? Atmosphere means, because our Earth atmosphere, say, because of friction, it gets heated up, and then the asteroid itself may melt, basically, in our sky itself. So this also, they give aerodynamic crushing stresses, say. So the equations are there, okay? How much, the crushing stress will be on the material in the atmosphere itself. I think this is very important for, that earth impacts also will give you, like, how much, how much it will be there, and then atmosphere blast or something also you can calculate from this equations itself, okay? So like this, we have a lot of things. Then, the dispersion of cluster of fragments is the expected dispersion. Also, these type of equations are there, which you derived for Earth. Of course, that same thing that Earth Impact program also uses. So this is a very important thing. So atmosphere blast wave, actually, when it blasts in the atmosphere also, you will have a blast waves. Thermal radiation also will be there. So it was like you see in Siberia, 30 to 50 meter diameter only, very diameter stony material, basically, it, of course, 2,000-kilometer trees and everything have been burnt, actually, due to this atmosphere, the blast, and then, which happened here. So this also, that Earth Impacts program, say, that the software, it gives you all these details itself. So you try this for those three craters and try to estimate all the input parameters. You can take, you can submit it also. Now, another most important thing is morphometry, actually. So morphometry, one is a dimension analysis. Morphometry means, now all of you have the QGIS, you have downloaded the topography data for Moon, Earth, Mars, everything, data is there. So what people have done is, so you identify all the craters, the diameter of the crater, depth of the crater, and how much is ejecta, how much it has gone, all those details people have found out. And then some type of equations people have fitted, like, y is equal to a d to the power of b. A and b are constants. So d is the diameter of the crater, basically. So y is, how depth is correlated with the diameter, then rim height, then ejecta, all those things. So simple equations also have been derived from the data. So this is what we call as morphometry. So please remember these words itself. So morphometry is nothing but some type of regression equations, okay, or some type of relations. So just from the data, no scaling laws, no dimensionality, nothing. So you go to that QGIS, you just observe all the craters, you find out its diameter, rim, all the variables, and then you try to develop some kind of equation, regression analysis. Generally that is what you try to do in our when you have a lot of data itself. So of course, one thing, the multi-ring basins, people have still not understood. because multi-ring basins, the data is very few. On moon are, where one or two or maybe some few basins are there. So it's very difficult basically, but simple and complex, so we can easily estimate these things. So I'm showing you, people have estimated, like this is in moon itself. So Tycho crater is there in moon. So if you go to QGIS software, say, and I hope all of you would have downloaded the topography data of moon, and then, if you can easily measure the diameters. Okay, so the Tycho diameter is 85 kilometers approximately. Of course, it has some kind of error. And then depth is 4.7. And of course, error they have, given this one. Then Aristotle's is 87 meter. Then, Compton 162. And then what is the largest basin on moon? Largest basin is none. Now, can you read here? What is the largest basin? If you see in these tables,
South Pole at
South Pole Aitken. So its diameter is how much? 2,500 kilometer, and here is the depth of the basin itself. Okay. And now, what is your interesting observation? Can you see here? Now, last class also I showed you. Just see the diameter, and then you see the depth. Say, what is that important thing you can observe? Now, what is important when you look at the data set? What is your feeling? Yeah. So like King Basin, if you see, say, diameter is 77, depth is 4.5. If you say South Pole, say, diameter is 2,500, almost it is 5 times or 8 times, or not 10 times or more than that one. So 10 is 770, you followed, right? Maybe 20 times or 30 times diameter has increased, but what about the depth? Diameter is increasing 20 times or 30 times. But what is happening to the depth of the crater?
The depth doesn't increase that much.
4.5 to 8.5. Last class also we discussed, right? Depth is not that much varying. So this has been observed for the moon itself. And now you have the data set. What do you try to do? So when you have got all the depth, now I'm showing here only diameter and depth only. But in QGIS, you can easily find out rim height, then the ejecta, how much distance ejecta can be seen, all those things you can extract from the QGIS software. So once you have all the data set, what is that you try to do? So generally, what do we do? The temptation is you try to see the relationship between all these variables itself. That is what we are calling as morphometry. Okay. So morphometry is nothing but, so like here, what we are trying to is, so now I know the diameter, I know the depth itself. Just to try to plot it, So if you plot depth versus diameter, say, of course, if you have to plot in log-log graph, that we have to decide. Like if you plot in an ordinary scale, you may not see any pattern. Sometimes semi-log, log-log, people try a lot of things itself. And because it clearly shows, diameter, if it is increasing by 20 times, a marginal increase only. So log-log graph, if you try to plot, say. So this is how the data looks like basically. So now here, you can see the transitions basically. Okay, so he says plus, I think, I don't know, plus these are all, the complex craters. That's what he says. Transition craters also are there. That is the open circles or whatever. And basins are, I think, the solid circles, whatever he has said. So now he has fitted some type of a equation itself. So this is our equation. Log 10d is equal to 0.41 into log 10d to the power of 0.457 itself. So some simple equations people have fitted actually. So these equations is valid only for moon. So if I know the diameter of the crater, say, so automatically I can find out the depth itself. So this is what we call as morphometry. Okay. So these type of studies also one can do, and all of you, since you have already downloaded the data set, so your first assignment is that the lunar basin and lunar crater and others, you have to find out the inverse problem. Now, apart from that, moon, since you have downloaded the topography data, you try to identify all the craters on moon, and then you try to fit these type of equations only. This is only, he has fitted only for few things only, just a few things only they have fitted here. But what to do is, for the entire moon, say, you try to identify all the craters, diameter, you can identify depth only, not only depth, you can extract more number of features itself, and you can fit these type of equations itself. Okay. So these sometimes, that's what they say. Depth you can find out from QGIS, rim height also, rim diameter, floor diameter, interior volume. So you can easily identify from those QGIS. Then complex craters are there. So depth, rim height, diameter of the central peak basically. Okay. Then basal area central peak, height central peak volume itself, then interior volume. Then if it is a basin, say diameter ring in central peak and peak ring basins, diameter inner ring, diameter inner ring. So you can measure all these things from our QGIS software. So once you get these type of things, you can fit some type of equations itself, like y is equal to a d to the power of b. So you can extract these type of equations, okay, and then you can compare these equations with Earth equations. Same thing you do for Mars, you do for Venus, you do for Mercury or whatever, and then you derive these type of equations, and then if you plot them in one graph, basically, okay. So now that graph will tell you, what is the difference between all these planets itself, the coefficients A and B. They will tell you how cratering, the diameter or the morphometry or the morphology of moon, how it is different from morphometry of Venus or other planets itself. So these type of equations are also very extremely, important in to understand the geology of the planets or the evolutions of this impact craters itself. Okay. So now to just keep it this one. So now the most important thing when you have impact cratering is one is a scaling loss. Okay, which comes from dimension analysis and others. Other one is morphometry. This is the second thing. Okay, so where you collect the data, you try to fit some type of equations, and you compare same type of equations you derive for variety of the planets, or you can even do these type of equations, like near side of the moon, then far side of the moon side. You can derive these equations and you can plot one by one the same graph, and then you can easily understand what's the difference between near side of the moon or other side of the moon, or the young areas, or the old areas. So these equations will give you insight into all these phenomena itself. So it's a very important the morphometric impact cratering. Okay. And now apart from that, another most important thing in our impact cratering is this the crater counting basically, or the size frequency distributions also. So what are the crater population basically? So what it says is the crater population, say, okay, how many number of craters are there? Like long back itself, I told you, if more number of craters are there, and we have a region where less number of craters are there. What did we say last week? No. If an area has more number of craters, say, what does it tells you?
It is older.
Older surface.
No, it is a older surface. Okay, so now, so the population, say, this also becomes very important to assess the age of our, this geological age also. Of course, you can use the morphometry also. You can use a crater scaling loss also, may give some type of insight. But this is a most popular thing is the crater population. So it is a very simple technique we try to use. Okay, of a long history of impact cratering events itself. So this technique is very, very popular even in our seismic, our earthquake analysis also. We call this as, you remember, I don't know, I think Kshitij, they would have not done the course in seismology. So we talk about Gutenberg Richter, log 10 n is equal to a minus bm kind of a thing. So, the B value, A value, we try to find out from the data, and they will tell you, which area, if the B value is low, say, that means, that region is active region, or in that region, say, you can experience a great earthquake in shorter time. And if the B value increases, so that means a big earthquake is not going to occur in that region. So like that, we have a lot of informations can be done. So the same concept one uses even in the impact cratering also. So the crater population, say like for example, this is a moon. Okay, so this is a mare which you can see in our naked eye itself. And these are highlands. Here, a lot of craters are there in this region, and here, there are no craters. Very few craters are there. I think that lava or whatever it has, maybe erosion has happened or whatever. So more later. So the analysis of existing crater population, say, in conjunction with some assumptions about the rate of crater formation, may reveal a great deal about the geological history of the surface. So this is a very, very important thing, the crater counting or the crater population itself. The flux, say, and the size distribution of impact bodies were known, studies of crater populations could yield absolute ages of the surface and some of its features itself. So if we know the size distribution of the impacting bodies, that is the meteorite sizes, if we can find out, we can even find out the geological ages from this data set itself. So the first steps, generally what we try to do is, in the investigation of a crater population, say, on a given surface is to select an area that is believed to have a homogeneous geological history. So like, for example, if I collect all craters on moon, basically, okay, and then I do the analysis, say, we may be doing a mistakes, basically. Why? So as already I told you, so like near said here, say, this area, this area may be young, you don't know, you followed it, and the highlands, say, maybe, it may be old, this itself. If I combine this data with this data and then I try to do analysis, say, we may end up with, the mistakes itself. The misinterpretation may happen on this data itself. So when you want to do this type of a method, say, you have to do homogeneous geological history. So this is the first step, you can do only for certain region, and then you have to test the homogeneities, how much spatial homogeneity and other things one has to see here itself. Okay, so that's what it says. Sorry. Yeah. So like you said, to combine the crater populations of a sparsely cratered lava plain with that of a densely cratered upland. So you can't mix this with this region. Okay, and if you try to mix, you may get some nonsense. Interpretations may come up. So homogeneity is the most important thing. Now, once such an area is selected, say, once you have selected an area, the craters that lie within it are counted. Actually, you start counting the craters, and most crater population studies include all recognizable craters, regardless of their state of degradation. Some craters would have degraded or whatever, so you count all the craters. Now, when a very large enough population exists, say, more specialized studies may be performed in which the number of fresh, like, if you have lot amount of data, so many craters are there, then maybe you can do, you can classify them into fresh craters, slightly degraded, and then maybe you can do a lot of analysis itself. But if you don't have more data, like so very few things are there, say, you take all the things and then you do our analysis itself. So this is what we try to do. And of course, the craters occur in a wide variety of sizes. So if you take any region, you may have a crater of 2 kilometer, 50 kilometer, very things will be there. So the principal information about a crater population is the number of craters per unit area as a function of crater diameter. So this is what we are interested. So if you select a region and then you count the number of craters and you divide by the total area of the region, say, and then you plot as a function of the diameter. So that is what we call as a size frequency distribution. And of course, the impact cratering, when a crater occurs, the crater formation, all those is a random process. Okay, so and there is no significance basically. Okay, so we are not interested in this one. We are looking only on the crater population only, and then its diameters itself. So there are several methods are there. How do we represent the data? Okay, so that you will get a nice, the information itself. So many methods are there. I will show you that one. One is incremental distribution, they say. Okay, so the numerous ways have been developed, you see. So is to list, say. So now when you are having selected an area, so you take a diameter, say. So now you classify diameters, like 1 kilometer diameter, 2 kilometer, 3 kilometer, 4 kilometer, 5 kilometer, and then you count how many craters are between 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, like that. You remember in your statistics course also, when somebody gives the data, say, like for example, I have a class strength of 100 students are there, and I have 100 marks basically. Okay, the marks of all the students, say. So what do we do? Or if you have done experiment and you have collected 1,000 samples itself. Okay, so what do we do generally in probability or in the data analysis, say, when you are having a 10,000 experimental data sets are there, what do you do?
We try to get mean, median, mode. Good to say.
That is a next level. You follow it. So mean, median, that is a next level. But what we try to do, the first thing, when you have 10,000 data sets are there. Okay.
So we remove unwanted data, which are not applicable.
No, not unwanted data. You don't know, right, which is unwanted or wanted. You have been given 10,000 data. So what do you do? When you
Sort
go
them.
start, huh?
Just sort them in any order.
Excellent. So you sort them, or in your school you have studied, right? If you have 1,000 data set, what is that you try to do? You try to plot a histogram actually. Of course, you do the sorting. That's what you do. Increasing order or descending order. That's what you told is perfectly correct. So what we try to do is histograms. How do you draw a histogram? Class intervals you have to do. You group, right? 10 to 20, 20 to 30, 30 to 40, and then you find out how many people are in this group, that group, this group. So we try to create the groups. So that's what is incremental distribution. So now you are having a craters, say 1,000 craters are there, and their diameter starts from 0.8 kilometer to some 50 kilometers. So you would now divide this into class intervals kind of a thing. So here we try to do, but here the problem is the class intervals is the problem is if you select a different class interval, you may get a different picture itself. Okay, so there's a problem here. So generally, I think I don't know how many of in statistics, if the data size is n, say, how many class intervals you have to take? Any of you have an idea? The bin size, how many bins you have to take? See, I have 1,000 data sets or 100 data sets are there. So how many class intervals I can go? Some thumb rules are there. Any of you remember? These are thumb rules. Like it's 100 data, how many groups I can create, or how many the class intervals? Any of you remember?
So 10.
For 10,000 also 10, 20,000 also 10. Now, what is a thumb rule? We study in our 6th or 7th statistics. One thumb rule is square root of n. Okay. So if you have 100 data sets, square root of 100 is 10. So the best is 10 class intervals you have to do. If you have 1,000, you have to take square root of 1,000. That is some thumb rules we have. Okay. So, and if you take 10 class intervals, you will get a different picture. If you take 5 class intervals, you will get a different picture of the histograms. So this is a problem in crater distribution. So what everybody does in crater analysis is, I will show you also. This is octaves they take. Okay, so octaves means you have to choose the bins like this. So D 2 times everything double. So if you have taken 1 kilometer, so then 2 kilometer, then 4 kilometer, then 8 kilometer, then 16, 32, like that it comes. So this is what we call as octaves kind of thing itself. So this is what they try to do, the binning, some guidelines are there. So they say that you can use the interval of D to 2D, something like that, you can do to draw to define your class intervals. And then these incremental, that's a histogram. Now the other thing is a cumulative distribution also. Like a cumulative, of course, what I think Kshitij or somebody told, like what do? You first sort the data into increasing order or decreasing order you try to do, and then you can construct a cumulative distribution function. That's also cumulative kind of thing only. Or you can do like you are having all the data set. You just find out, you take diameters, 0.1 kilometer, 0.3, 1 kilometer, 2 kilometer, and then you find out how many craters have diameter more than 1 kilometer, say. So you form a group. How many diameters have more than 2 kilometer, 3 kilometer, 4 kilometer, like that you add all of them. That is a cumulative kind of a thing, and that itself you can use itself. That's what we call a size frequency distribution also. Okay, so SFD, like that, you see, we do this one. Now the advantage SFD is these two are interlinked basically, incremental and size frequency. So incremental is nothing but a derivative only. You followed. So if you know the cumulative distribution, say DA, DB, you can subtract one among this one, you will get your incremental distribution also. So this also we try to do like integral kind of a format itself. And of course, cumulative distribution always you may not get a nice feeling because derivative will give you the small things. It will zoom and then you will get a nice things itself. So this is what we do. So now here I'm just showing you one example, typical example. I think this is Mare Solovsky. Okay, I think some crater, I forgot where, I think moon or somewhere it is there, this is a crater. So now they want to do the age or this one. I think the Japanese Kaguya, this is a camera that from that they have located. And now what he has done, can you see here? So he has selected a region. So what is that? We said uniform geological region. So he selected only this Mare basically. So these are lava, whatever he has selected. Can you see this graph? Small craters are there. Can you see here? These yellow circles, you say. Apart from that, small craters also are there. So what you have to do is you have to count all these craters itself, and you have to find out its diameter also. And then this is the area there. And of course, this region, say the central peak or whatever he has maybe excluded or whatever here. So this is his area basically. Okay. So now you count the number of craters, say, and then you divide by the area of this region. You will get the density or whatever you have this one. So that is your cumulative crater frequency per kilometer square, because it has been divided by this area. So this versus the diameter of the craters he has plotted here. So this small region, say, that is Mare Solovsky. Okay, I think it is D is more than 750 meter he has taken here. and then this is his graph, looks like. So you can see these these black squares. So this is what he gets in this region actually. So this is what we call as, the size frequency distribution or cumulative frequency distribution. So what you have to do, he started with 750 meter. So how many craters are more than 750? How many craters are more than 755? 1 kilometer, and he has gone up to, I think, this is a 1, and this is a 2 kilometer or whatever, he has identified. So this is a cumulative plot. Now, if you differentiate these plots, you will get, see the cumulative thing, if you differentiate, what do you get? So if you differentiate, what happens? You will get, you remember, right? In probability theory also, cumulative distribution function is there. If you differentiate cumulative distribution function, so what do you get? See, CDF. So if you differentiate a CDF, what do you get in probability?
So density function.
Density function only. Excellent. Okay. So here also, the incremental thing. So same, both are same only. CDF, PDF, whatever you have studied. So this is like if you take this as a CDF or whatever, say. So this is a derivative of this one. So this is the plot it looks like actually. Okay. So you can see. So these plots, it nicely, because of course he has taken bins and then he has done. That's why the numbers are very, this 1, 2, 3, 4, 5, 6, 7. It has come actually. Okay. So this is how it comes. So these are the two graphs: relative frequency or incremental distribution, and then cumulative size frequency distribution. So these are the two how we construct from this data set itself. Now, how to do this one? There is one standard. The reference is there. Okay, we can't do. 1979 NASA has published. I will just share you. You can see this thing. Can you see this document? Is visible?
Yes, sir.
So this is a NASA's technical memorandum you followed. So standard techniques for presentation and analysis of crater size frequency data. So in 1979, they released this document, which is, it is something like a benchmark kind of thing. So if anybody wants to do the cratering analysis and if they want to present the data, so they have to follow this, this manual itself. So the cratering, this group is there, one big group here, which is done by this NASA. So this one, that's what they call as a cratering analysis techniques working group actually. Okay, so which is done by the Washington NASA, that Washington office or whatever. It was released in 1979. So I will, of course, you can get it in Google, and of course I will be sending you also. So this is a document which clearly says that how to present the data, how to handle the analysis also. Very nicely written, the document itself. Okay, of course, the same cumulative, that size frequency. So all these things have come from this document itself. So if you see this, same thing you have put up in PowerPoint. Okay. So this I have extracted from the PowerPoint. So what he says is the cumulative size frequency distribution plot. Okay. So they have given nicely the definitions. Of course, it's same only. Whatever we said, possess a number of what is important attributes he has given. Then bin size. This doesn't come in cumulative for this type of plot itself, because here you take the data, you just take how many number are more than 0.1, 0.2, 0.3, 0.4, 0.4 like that. So the bin size and other things doesn't come into picture. So they give what is the pros and cons for each plots itself. Okay. And then you see how do we construct this one. So what they say is the methodology they have given. Okay, unbind data, bind data also. Okay, so like the best they say is unbind actually. You just take the raw data and then they say like sort the craters into descending order by diameter. Okay, so the largest one is D1, D2, D3, D4 basically. Now plot the log of diameter of each crater. So that is log of Dn against the log of total or cumulative number of craters per unit area with equal or larger diameters, log of n by a, where a is the surface area. Okay, so you have to count. So you take diameter D1, say how many craters are more than D1. Okay, and you divide by the area of that region. Now you have to find out how many number of craters are more than D2. Okay, so then you divide by area, you will get the number. So like this, you collect the numbers and then you plot as a function use log of this one versus log of D itself. So that is what they say how to construct, this size frequency distribution cumulative thing from the data, and these unbinned data from the raw data. Then you can also find out from the binned data. Binned data means, you have the data, the creator's data you have estimated, and then you have done this class interval business itself. So you don't have access to the original data. You have only the binned data. Like, somebody has divided this into 5 class intervals, and they have given, like, in this class interval 50 creators are there, 20 creators are there, 30 creators are there. Now from this, how do I construct a size frequency plot itself? So it's straightforward only. It's very simple. So it says to plot the data, say, in bin 1, which has bin I, which has a diameter limits from dA to dB, say, because the class interval has and contains ni creators. It's a plot log of rho, where rho is, nk by ak, I is equal to k to 1 to I itself. Again, it's log of dA. So this is what they say. You can construct from bin data also. You can construct from unbinned, the data itself. Okay. And then the relative size frequency distribution, say, of course, it says a lot of other things are easily implemented. You construct from these two procedures, and then how do we plot this? Okay, so they say, like, you have to do it systematically. The methodology, say, very simple, straightforward only. And then if you want to the increment plots, incremental things also, they use this expression, that is R. So d power cube n by a into dB minus dA. That's the derivative of our size frequency plot itself. So this you find out, and then you plot the data itself. Okay. So and of course, all the tables, they say, if you want to do this analysis, you have to give everything systematically. Okay. All the data should be binned, and they also suggest basically the bin should have a geometric width of not greater than root 2 1.414 kilometers. Okay. So like bins is 1 by root 2 to 1, 1 to root 2, root 2 to 2. So they have nicely given the how to choose the bin size. Everything has been given. Okay. And how to prepare the data also they give you, and supporting information I will just to show you, like other, and then analysis also, morphological analysis, they give all the systematically how to do. So this is what they say. So you display the data, say, both cumulative size frequency and relative size, that's incremental thing, and makes abscissas ordinates both base 10 logarithm you have to use it, and consistent units have to be used, like kilometer kind of a thing, same scale, confidence levels you have to be in, and then tables, say, this also you have to prepare in a systematic format actually, and supporting information has to be given. So just to show you one example, say, okay, so this they have taken as lunar mare, basically front side post mare. So this is a data set, and this is a binned data you followed. So like bin diameter, so 8 to 11.3, how many number of craters per bin basically, and here's the area in which they have calculated. So 11.3 to 16, so 60 craters are there. 22.6 to 32, 19 craters are there. And this bin size also, that memorandum gives you a guideline, root 2, or they have given some classifications. So based on that, the bin sizes has been done. And now when you go to the large diameter, say, so generally how many are there? Now, can you see here large things? How many are there? Now, see large diameter crater, how many are there in this region? Now, all of you are, what is the largest diameter in this post this region?
128 to 180.
180, only one is there. Okay. So generally, when you see the craters, they have a nice pattern. Small size craters will be very more, so many will be there, but large size, they decrease basically. Only one few things will be. This is one place. Now this is eastern part, actually, Mare Crisium they have done. Some other crater also. See here also, bin diameters, number of craters have been given. But here, they have, I think this region, the craters have not more than 3.6 kilometers. So this region has a huge, big craters, but here you don't have these craters. Now, once you have got all the data, say, now you plot it. So this cumulative distribution is like this. So this is region A and this is B. So you count them, and then you have to do a cumulative kind of thing. So cumulative means what you have to do is, so you have to add 91 plus 60 plus 22 plus 19 plus 7, 6, 2, 2, 1 like this. Then you understand, right? So finally 60 plus this one, then 22 plus 19 plus this one, and finally in the end it will be only this one itself. Okay. So like this, you will have all the plots itself. So this is for the region B and this is for the region A versus diameter. So this you have to plot it basically. Okay, the area this one, and this is a R plot. That is incremental plot. So this is for the region B and this is for the region A. You follow? So this is how to construct these things, so that NASA's technical reports it nicely it's a very simple thing only, but they have done so systematically that they will not do any mistakes basically. And then many people say interpretations will be difficult, so they have the unified framework they have developed in long back, and now also it's widely used in all the planetary explorations to understand this impact craters itself. So fine. So I will stop here. We will continue in our next class. So if you have any doubts, you can ask.